So I've got an application I want to take a look at, coming back to that tangent line slope stuff. But before that, I had one last example I wanted to show you. So we've got what looks like kind of a terrifying function right here. F of x equals the 8th root of e to the pi. And so if we wanted to calculate the derivative of that thing, you might end up trying a fair amount of stuff. It's like, okay, well, we've seen that we can turn roots into fractional exponents. Rewrite this as like e to the pi over 8, and then you might end up sort of like, is this a power function? Is it an exponential function? Like, which of those rules applies? Yeah, psych. Yeah, this is actually a trick question. So this says this is a function of x. Is there an x in here anywhere? I don't see one, and even with my bad handwriting, I can assure you that's supposed to be a pi, not an x. For all of this notation, this is really just a number. That means this is a constant function, and according to our very first formula on the Bestest Friend sheet, its derivative is 0. This thing doesn't have a variable in it, so be careful. That's one of those things that sneaky math professors like to sneak in as, no pun intended, I used the same word twice in one sentence, like to sneak in as kind of like a trap. Do you fall for like trying to pull this and write the derivative as like, pi e to the pi minus 1 or something like that? No, it's just 0 because there is no variable. As far as x is concerned, this thing just sits still and does nothing, so its derivative is going to be 0. All right, about that application. All right, so again, trying to link back that whole derivative tangent line slope thing, you could do a similar exercise with velocities, if you wanted to. But so I give you the graph of this function here. So y equals 2x cubed plus 3x squared minus 12x plus 1. And I ask you where that has a horizontal tangent line. So where you might say find points on the graph with a horizontal tangent line. So yeah, that's fine. So if you imagine, you could take this guy, pop him into your calculator, and sketch a graph and find the places of the horizontal tangent. I'm not going to do that here, but just as a reminder, I'm going to give you an awesome rendition of what a horizontal tangent line is going to look like. It's going to look like that. Yeah, it's nice and flat and boring. What's the slope of that flat, boring line I'm making with my arm? Yeah, it's 0. Horizontal lines have a slope of 0. And since we've already said the circle of calculus tells us that tangent line slope and derivative are in fact one and the same thing, so I'll just call it y prime. Normally I would write like dy dx, but you get the idea. So now we need the derivative of that thing. So thanks to our the newfound power of the Bestest Friend sheet, rather than having to pound through this as a limit calculation, 3 comes out front. 3 times 2 is 6. 6x squared. That 2 comes out front there. 3 times 2 is, again, 6. X to the first minus 12x. The derivative of x is 1. So minus 12. The derivative of 1 is 0. He's a constant. He goes poof. So that's what our derivative looks like. We need that to equal 0. Now, at this point, this thing is a quadratic. What do we do with quadratics? Yes, quadratics exist to be factored when these things come up. That's not really true, but you get the idea. It feels like that's what we're always doing with them. If you'd use the quadratic formula, that's also fine, but so I can factor 6 off this thing, because all of those numbers are divisible by 6, so you'd have x squared plus x minus 2. So we have x plus 2, x minus 1 equals 0. So our two target x coordinates are x equals negative 2, because again, you got to change the sign when you set this thing equals 0, or x equals 1. Those are our x coordinates. Often, though, we'll ask you, like I said, where means like a point on the graph of the function, so we actually just have the x coordinates. We need to find the y coordinates. So if you had just said x equals negative 2, x equals 1, you've got half of what you need. Now you need the y coordinates. Sort of like what we said with that max height problem before, though, don't fall for what feels really tempting and just try to plug those values back in here. By design, you're going to get 0. And those points, spoilers, they don't live on the graph of this function. We actually need to take x equals negative 2 and x equals 1 and plug them back into this bad boy right here. So that's the kind of thing where, yeah, it's perfectly reasonable to type that into your calculator's Y editor and let the table feature do the number crunching. So as it is, if we plug in a -2 to this thing, I'll leave it to you to check. But when I worked that out, I got -2 and a y coordinate of 21. If I plug 1 into this thing, it's a lot easier for me to do the arithmetic in my head because it's basically just the coefficients plowed through, right? 2 plus 3 is 5, minus 12 is -7, plus 1 gives me a -6. So those are my points with a horizontal tangent. Sometimes problems like in web work may just ask for X values where something like this happens. Yeah, be on guard. But we try to set up via context whether you're supposed to put in like X, Y pairs or not. But so yeah, that's an application of this stuff in action, and it's way quicker when you can just use the bestest friend to come up with your derivative formula instead of having to fall back on the limit definition. As I said, there are times you need that limit definition, and I can promise you we'll check to see if how comfortable you are with it. But yeah, so I think it feels more comfortable for just about everybody who takes calculus to take this approach. All right, one last concept before we draw the section to a close. All right, last point for the section. This technically kind of bleeds into the next section, but I want to go ahead and tuck it in here while I've got time and I'm thinking about it. I'm bad about overlooking this and then kind of getting caught flat-footed when I haven't mentioned it later. So you'll often hear this thing we've called the derivative so far. You'll sometimes hear textbooks or math teachers like me refer to it as the first derivative of a function. That kind of implies that there's something we call a second derivative. As it turns out, there's actually a whole lot of them. We'd refer to these as higher derivatives or higher order derivatives of a given function. And it turns out it's an idea that you're probably kind of used to from your math classes. Most of our operations, we kind of end up seeing what happens when they stack up on each other. Like when you first learned how to multiply numbers together, you thought of like repeated additions, right? Or exponents are like repeated multiplications. That same principle. Derivatives are the same way. They kind of stack up on themselves. So if we talk about the second order derivative, or simply the second derivative of a function, f of x, so we normally denote that second derivative f double prime of x. So we have two of those not quite apostrophe looking things. But it turns out, again, it's just an iteration of the principle. So we come up with our first derivative, the f prime that you've seen me work with, and then we take a derivative of that thing, of the result. So second derivative, we did a derivative twice. So you can have a third derivative. Then we would take the derivative of this thing to get f triple prime. Generally speaking, once you go past that third derivative, if you have a bunch of them hovering around, yes, they do occur in applications. It's beyond the scope of Math 115. So you usually stop representing these with primes just because by the time you've got like 6 or 7 of them, it's kind of hard to keep track. So you'll often see like a parenthetical thing with a number telling you how many derivatives you've taken. It shouldn't be much of a factor for this course, but in case you're poking around on the internet, that's what that means. If you see like f with a 2 in parentheses of x, that's a second derivative. So if I gave you just a relatively boring quadratic, like x squared plus 3x minus 4. And its first derivative we can bust out using our power rule techniques. So I get, 2x plus 3 out of that guy. Then if I wanted the second derivative, now I zero in on him. I don't actually even need this formula anymore to get, f double prime of x. I just need the derivative of this guy right here. And for what it's worth, now the 3 is a constant. His derivative is 0. The derivative of 2x is just 2. So the second derivative of my function is just the constant function 2. If I took a third derivative, then I've got the constant 0 function, which is less exciting. So this same sort of thing comes up in applications. You'll recall we talked about acceleration being the derivative of velocity, which was itself the derivative of position. So you can actually interpret acceleration of an object in motion as the second derivative of its position function. So just like I said, planting the seed there. So when I talk about second derivatives later, it's not a Professor Carroll, you didn't mention that. So that's it for this section. Like I said, the bestest friend is really awesome, and he greatly expedites the how we can go about calculating derivatives of functions once we have all of those tools in place. But you may notice that there are some combinations of functions that I have like pointedly avoided. We'll talk about those in the next section.